which is Ellie Mullin from University of Michigan. Her presentation will be on still beam cube characterization for mini neutron scatter camera. Go ahead, Ellie, if you are ready.
Okay. Can you see my screen okay?
I can, yes.
Okay, wonderful. So hi everyone, my name is Ellie Mullin. I'm a PhD student working with Professor Pozzi, and I'm just finishing up my first year. Today I'll be talking about the still beam cube characterization that we performed for a mini neutron scatter camera. So first, just a little bit of introduction and motivation. We know that neutrons are emitted from special nuclear material, or SNM, either passively or when this SNM is actively interrogated with other forms of radiation. We also know that neutrons are not significantly present in the background radiation like gamma rays. So when we detect neutrons, we can be pretty sure that we're also detecting the presence of SNM, which is why detection and localization of neutron sources is really valuable for determining the location of SNM. So to localize neutron sources for many applications, we need small and portable systems. Some of these applications include emergency response, warfighting, etc. And so we're kind of exploring this mini neutron scatter camera, which utilizes silicon photomultipliers because it offers this small and compact capabilities that we're looking for. So what does our mini neutron scatter camera consist of? The first aspect is a silicon photomultiplier. These are Geiger mode avalanche photodiodes, and you can see an image of one of these in the top right of the slide. These are compact, they're low voltage, not much magnetic shielding is required, and they have been shown to have comparable timing and pulse shape discrimination, or PSD, which I'll talk about later, to photomultiplier tubes, or PMTs. We are also coupling still beam cubes to our SIPM arrays, and these still beam cubes that we're using are small, so they're 6 by 6 by 6 millimeters cubed, and you can see an example of a still beam crystal in the bottom right photo on the slide. Still beam cubes have excellent timing properties, they have really excellent pulse shape discrimination capabilities, and they have very efficient light output. So how does a neutron scatter camera work? We have, let's say, a neutron with energy E coming in and interacting with one of our detectors. In our case, this would be one of our still beam cubes. So the neutron comes in, interacts in detector 1, and we can measure the energy deposition, the location of interaction, and the time of location in this detector. Then let's say it has a double scatter, so it scatters in our second still beam cube. We get the energy deposition, the location of interaction, and the time of interaction in this second detector. So then using simple kinematics, we can solve for the velocity of this neutron and then calculate its time of flight energy using these equations in the middle. And if we add this time of flight energy to the energy deposited in the first detector, we can reconstruct the incident neutron energy. Additionally, we can calculate an opening angle or a cone, which you might have seen in presentations earlier today, using the time of flight energy over the incident energy. And once we have a bunch of cones that overlap, we can determine actually where this neutron source is. So to characterize our mini neutron scatter camera, or to better understand the capabilities of our neutron scatter camera, we need to do a few things. We need to be able to calibrate from our pulse integrals that we measure to the gamma ray light output. We need to be able to discriminate between neutron and gamma ray interactions within our detector, so we use pulse shape discrimination, or PSD. We need to measure the time resolution, the energy resolution, and the neutron light output. So for the purpose of this presentation today, I'll just focus on the first 3 characterizations that we've performed thus far. So to do these, that I mentioned on the previous slide, we performed several laboratory measurements. And you can see our setup in the photo here on the right. And you see down below are our still beam cubes wrapped in Teflon, and these are coupled to our Sensel J-series SIPM array. So like I mentioned before, we wanted to calibrate our gamma ray light output, and for this we used a cesium-137 source. We placed it about 10 centimeters in front of our detector and measured for 30 minutes. Then to perform pulse shape discrimination or perform this optimization so we can really discriminate between neutrons and gammas, we used a californium-252 source and measured it in the same fashion that we did the cesium-137. Then it was necessary to measure the time resolution of our two Stovene cubes. So we performed a coincident measurement using the sodium-22. You can see here where my mouse is, this is our sodium-22 source that we placed between our Stovene cubes, and we measured the two 511 keV gamma rays from this source. So first I'll present the results from our californium-252 measurement, which, like I said before, we did to perform PSD optimization. So pulse shape discrimination utilizes the difference in pulse shapes from the neutrons and gamma rays that interact in our Stovene cubes. We take a tail integration region and a total integration region shown in the bottom left plot, which just shows the raw pulses from one of our californium-252 measurements. And you can see the tail and total regions of the pulse marked on the plot. We then take the ratio of tail to total, and we get different PSD ratios for neutrons and gammas, as you can see in the bottom right plot. So we get a peak if we histogram all of these PSD ratios for neutrons and gamma rays. Then we can tell actually how well our system is differentiating or separating these two peaks using the figure of merit, or FOM, which you can see in the top right equation, which is just the centroid of the neutron peak minus the centroid of the gamma ray peak over the full width half max of both peaks added together. So this gives us kind of a quantification for the separation between the two. And here I just am showing the PSD ratios as a function of energy in keVEE for both cubes. And you can see that we really can differentiate between the neutrons, which is the top band in the plot, and the gamma rays, which are the bottom band in the plots. And just to go back to figure of merit values, to quantify this separation, we split up our data into two different energy ranges, so 50 to 100 keVEE and 100 to 150 keVEE, and calculated the figure of merit for both cubes in both energy ranges. And you can see that we have a figure of merit that's greater than 1 for all energy ranges in both cubes. So this is, these are really sufficient in separating neutrons and gamma rays. And for anyone who's interested, our tail integration region that we optimized ended up being 60 nanoseconds past our maximum of every pulse, out to 400 nanoseconds of each pulse, and our total integration region was the maximum of each pulse out to 400 nanoseconds of each pulse. So next I'll move on to the results of our sodium-22 measurement. So because we're measuring the timing of these pulses, we need to figure out when does our pulse actually start that we measured, what's the timing. And for this, we use digital constant fraction discrimination, or DCFD. And we actually need to optimize this fraction. So if you look at the plot on the bottom left, this is a raw pulse from one of our sodium-22 measurements. You can see a star in the bottom of the pulse there, and that represents 5% of the pulse height. So we take a certain fraction of our pulse height, and then we interpolate between our two digitized points of this wave, and we find this fraction of the pulse, and then this fraction represents our time of the pulse. So we take this this fraction as the time for every pulse, and then we look at the full width half max of our time distribution. So we make a histogram of all of these time differences between the two cubes and calculate the full width half max, because we say that the full width half max is representative of the timing of our system. And you can see in the bottom plot, we plot the full width half max as a function of the DCFD fraction. And as we increase the DCFD fraction to higher values of the maximum of the pulse, we get higher full width half maxes. And so we found that our optimal DCFD fraction is actually 5%. And you might be asking, why don't we use this lower DCFD fraction, because it gives us a smaller full width half max value. But if you look at the plot on the right, you can see that at lower, well, this is a plot of the percentage of bad start times, or the percentage of times where this star actually lies on the baseline and not the rising edge of the pulse. And you see that for lower than 5% DCFD fraction, we get greater than 20% of our start times actually lying on this baseline instead of the rising edge of the pulse. So we didn't want to use all of those bad start times. So this plot here just shows our time difference histogram over all of our energies with a 5% DCFD, and you can see the full width half max here by the arrows. We calculated a full width half max of 250 picoseconds over all of our energies, and if we gate on the Compton edge, so that's about 240 to 390 keVEE, we get a full width half max of 160 picoseconds. So these are really small full width half max, excellent timing resolution. So just to recognize the MTV Impact, it has provided many opportunities for my participation in workshops and conferences. Additionally, it has allowed me to work with national laboratories, so a collaboration with Sandia National Laboratory for much of this work, and I'm doing an internship virtually at Los Alamos National Laboratory this summer. So in conclusion, based on this pulse shape discrimination and timing resolution characterization, we found excellent PSD and timing resolution. And we believe this is sufficient to successfully image neutrons, and therefore the mini neutron scatter camera could be a viable technology because it's compact and portable to image neutrons in these kind of applications. And this photo here just shows an experimental setup with 3 Stobine cubes coupled to our J-series SIPM array. So some next steps will be to perform additional laboratory measurements. Like I said on one of the previous slides, we only performed the top 3 bullet points for our characterization thus far, so we want to measure the energy resolution and the neutron light output so we can actually start imaging neutrons. And then we'd like to perform simulations of the mini neutron scatter camera and populate it with 8 Stobine cubes, which is what we'd like the eventual neutron scatter camera to have. And so lastly, I would just like to thank the NNSA and DOE for funding MTV and my graduate research, and I can take any questions. Thank you.
Thank you, Ellie, for the interesting presentation. Are there some questions from the audience? Let me see. There is a question, is there a special reason to use steel bin cubes rather than bars, other than size, footprint of the detectors?
That's a good question. Well, yeah, the size and the footprint of the detector is a really motivating reason to use the Stobine cubes, but also we're looking into the uncertainty as well in our timing and location of the Stobine cubes in comparison to the Stobine bars. So that might be another motivation for using the Stobine cubes.
I remember we had a discussion in the previous session on the comparison between cubes and bars. I remember that maybe that was Nathan or someone I asked the question. What I remembered was ruggedization is one consideration, and also the uncertainty in the position. I would imagine, okay, I'm still thinking about the difference between cubes and which is basically like one layer of cubes and a bar. So the bar, I would imagine you could make like 5 or 6 cubes to make a bar, but the light is transparent in between, but you have segmented cubes, right? Then you read the light from opposite sides of the cube made up of the bars. Then you still have the same uncertainty. It's like as long as you can tell which bar, which cube the light originally come from. And would that something be interesting to think about?
Yeah, that would be really interesting. I never thought about stacking them and maybe having like SIPMs on each side or something, and then you could even get less uncertainty. So you can use the 2 sets of silicon PMTs to read out. So you double the readout, but you can make many cubes that you can reduce the total number of readout in your system. So that's something. Yeah, and the H2 DPI that Will presented on, they do the dual readout on the Stobine pillars. So.
There is another question came in. Do you have a sense of energy resolution at around 1 MeV, I guess, neutron energy?
I don't have a sense of the neutron energy resolution because we haven't been able to perform measurements for the neutron, for the energy resolution yet, but we will. So then I will have an answer for you.
Okay. Are there other questions from the audience? We have quite some time. We are 10 minutes ahead of our schedule. Thank you for the presentation.
Thank you.
If not, let's move to the next student.